Whenever you're driving down a highway that's been blasted right through a mountain, do you ever stop and think, how on earth did they do that? Well, the roads and railways we take for granted are built on a scale that is just mind-boggling. And at the heart of it all is this massive hidden logistical puzzle. So let's dig in and see how engineers actually solve it.
It seems like a pretty simple question, right? But the answer is incredibly complex. I mean, you can't just pave over whatever's there, over the hills and valleys. You need to create a path that's smooth and relatively level. And that means moving millions, literally millions of tons of earth. So where do you even start?
Well, when you boil it all down, it's really just a simple balancing act. To flatten out the landscape, you're doing two basic things. You cut into the high spots, digging out all that dirt and rock. And then you take that same material and you use it to fill in the low spots. It's kind of like the world's biggest cut and paste job.
But here's the real billion-dollar puzzle. The digging itself, that's not actually the most expensive part. It's the moving. Every single truckload of dirt costs money. We're talking fuel, labor, time. So the absolute number one question for engineers is this: how do you move the least amount of dirt the shortest possible distance?
This is not a problem you can just wing. When you're managing a project this huge, you need a master plan, a map for every single cubic meter of soil. And believe it or not, over a century ago, engineers came up with a surprisingly elegant tool to do exactly that. And this is it. It's called a Brückner curve. Now, I know, it might just look like a weird, squiggly line graph, but to a civil engineer, this right here is a roadmap to saving millions of dollars and building our world as efficiently as possible.
To put it simply, the Brückner curve is basically a running tally of the project's soil balance. From start to finish, it tells an engineer exactly where they stand. Do they have a surplus of dirt from digging up a hill, or are they in a deficit because they're trying to fill a valley? The whole point of this thing is to make logistics as cheap and efficient as humanly possible.
Okay, so what's really cool is how this thing actually works. It looks a little intimidating, but the rules for reading it are actually super simple. Let's break it down.
So first you've got your axes. The horizontal one, the x-axis, that's easy. It's just the distance along the road. Kilometer 1, kilometer 2, and so on. The vertical y-axis, though, that's where the magic happens. Think of it as your project's soil bank account. If the number is positive, you're in debt. You need more dirt for filling. If it's negative, you're in surplus. You've got extra dirt from cutting.
So here's rule number one. When you see that line on the graph going up, it means you are in a fill section. You're dumping earth into a low spot, raising the ground level. This makes your soil debt go up on that y-axis. Simple, right?
And rule number 2 is, you guessed it, the exact opposite. When that line starts heading down, you're in a cut section. You're digging into a hill, which gives you a supply of dirt. This brings your soil balance down, and once it crosses that zero line, you've officially got a surplus of material.
And this is where it gets really brilliant. The graph creates these peaks and valleys. The downward slopes, the cuts, are where you get your dirt. The upward slopes, the fills, are where you need the dirt. The whole game is to move dirt from the peaks of this graph to the valleys, over the shortest horizontal distance possible.
Now, this brings us to the one number engineers are obsessed with minimizing, the Hall moment. It's just a fancy term for a simple idea: the volume of dirt you move times the distance you move it. Think of it as the total cost for all of your dump truck trips. And on this graph, the Hall moment is literally the area inside these loops. So the smaller the area, the cheaper the project.
But in the real world, things are almost never perfectly balanced. So what happens when you have a bunch of dirt left over? Or even worse, you run out? Well, the curve has an answer for that too.
This is the big question every single project manager has to deal with. At the end of the day, do we have too much dirt or not enough? And what are we going to do about it? The final position of that curve tells you everything you need to know. Now, in a perfect world, the dream scenario, the project is perfectly balanced. You cut just enough dirt from the hills to fill in all the valleys. If that happens, your Brückner curve starts at zero, and after all the ups and downs, it ends right back at zero. It's beautiful, it's cost-effective, and it almost never happens.
Way more often, you get a mismatch. So let's say you've planned out all your cuts and fills, and you realize you're going to have a massive pile of extra rock and soil. What do?
This is what that looks like on the curve. If the line finishes its journey below that zero axis, it means you have a surplus. You dug up way more than you needed to fill. All of that extra dirt has to be trucked off-site to a special disposal area, which in engineer speak is called a depot.
Okay, now let's flip it.
Let's imagine the opposite problem. You're building a massive embankment for a highway. You've used up every last pebble from your cuts, and the fills still aren't done. You've run out of material. Now what?
On the curve, that scenario looks like this. The line ends above the zero axis. You have a deficit. You need more dirt than the project itself can give you. When this happens, engineers have to find an outside source, like a quarry, to get what they need. And this source is called a borrow pit.
So it's a really clever planning tool, for sure. But its impact in the real world is, well, it's massive. This is not just some dusty old academic exercise. It's a cornerstone of how we build the modern world.
So why does a graph that's over 100 years old still matter so much? Because it is the ultimate tool for efficiency. It balances all the earthwork, it finds the absolute cheapest routes to move dirt, and it tells you up front if you need to find a borrow pit or a depot site. For huge public works projects, this saves taxpayers millions, even billions of dollars. But it's more than that. It also dramatically cuts down on fuel use and the whole carbon footprint of construction. It is a key tool for building a more sustainable world.
So, the next time you're cruising down a smooth highway that cuts through a rugged landscape, you'll know it's not just a feat of brute force and heavy machinery. It's actually a beautifully solved math puzzle. And it kind of makes you wonder, what other invisible math is out there, quietly and elegantly shaping the world all around us?
Thank you so much for watching this explainer. We love breaking down complex stuff like this, and we do it every single week.
So if you enjoyed this, please don't forget to subscribe so you don't miss the next one.